Good morning. My name is Songshi from Beijing Institute of Technology. Today, I'm going to present our work, ProgrammabilityMedic, Predictable Path Programmability Recovery under Multiple Controller Failures in SD-WANs. It's a joint work with the researchers from Professor Zehua and Professor Yuanqing. My research focuses on software-defined networking, also known as SDN. There are many advantages of SDN. For example, you can see that the traditional networking cannot flexibly realize the traffic scheduling dealing with the congestion, but the SDN can flexibly realize the traffic scheduling by the SDN controller. A number of papers focus on the wide area network too, also known as WAN. WAN is a typical application scenario for SDN. Internet service providers operate their WANs to provide different services for downstream users. To reduce the operational cost and improve network performance, many Internet service providers, such as AT&T, have started to employ SDN to virtualize their WANs. A WAN usually has a large scale with many network devices. This slide shows a simple network of AT&T from topology 2. It's not easy to control such a large network with a single SDN controller. So, one promising solution is to partition the network into multiple domains and use one controller to manage all the switches in one domain to provide the quick response. These distributed controllers synchronize with each other to realize a physical distributed but logically centralized control plane. So one may ask, do we need to consider the control failure? Is it a critical issue? Does it occur frequently? The answer is yes. Essentially, an SDN controller is a network software. Since it is a software, it will have some software bugs leading to software failure. We can install an SDN controller in a physical server or virtual machine. Under unexpected hardware failure and power outage, the controller cannot provide normal service to the network, so maintaining the control resiliency for the SDN is important. One possible solution to control failure is to remap the offline switches to active controllers to recover the path programmability, but there are challenges. The control resource of active controller is limited, and we need to recover a lot of offline switches when facing the multiple failures. And existing solutions can be divided into two categories. The first is called switch-level mapping solution. For example, the ritual flow lets some offline switches work under legacy routing mode without the controllers, and the rest offline switches with the SDN routing mode. Thus, it can let them have more available control resource, but it has two problems. The first is the fixed control cost of offline switches cannot perfectly fit the control resource of the active controllers. And the second is the coarse-grained per-switch mapping. And the second one is the flow-level solution. For example, the Programmability Guardian introduced a middle layer between the controllers and switches using flow weather, so it can realize a fine-grained per-flow mapping. But the introducing of the middle layer can increase the processing delay and bring new unreliability. And the hybrid SDN routing and SDN and legacy routing mode provides us the opportunity to dynamically change the cost of the offline switches by selectively deciding the routing mode of each offline switches on the switch. We have three design considerations here. The first is recovering offline flows as many as possible. The second is balancing path programmability. And the third is fully utilizing the controller's control resource. And then we formulate flow mode selection and the switch mapping problem. This problem has four constraints. The first is each switch can be mapped to at most one controller. The second is the control load of the controller should not exceed the controller's available control resource. The second is the flow programmability constraint. And the third is the propagation delay constraint. And we have two objective functions. The first is to recover offline flows as many as possible and let them have the similar programmability. And the second is to make full use of the control resource of active controllers. Then we formulate the problem here. We all know that the typical solution of the above problem is to get its optimal result with IP optimization solvers. However, as the network size increases, the solution may cost a long time to find a feasible result. So, we will achieve the trade-off between the performance and the complexity and propose a heuristic algorithm to solve the problem. Our heuristic solution mainly have two parts. The first is perfectly recovering offline flows, which have the least programmability. And the second is making full use of the available control resource to improve the total programmability. We use a typical backbone topology named AT&T from Topology Zoo to evaluate the performance of the PM. The AT&T topology is a national topology of US and consists of 25 nodes and 112 links. In our simulation, each node is an SDN switches, and any two nodes have a traffic flow forwarded on the shortest path. The control plane consists of 6 controllers, and we have 4 compression algorithms: rich flow, PM, optimal, and PG. And the first figure shows the percentage of recovered flows. We can see that the PM, optimal, and PG recover all offline flows, but the rich flow can only recover 78 to 99% to PM because it's a coarse-grained per switch mapping. And second is the communication overhead. We can see that PG performs the worst because the introducing of the middle layers, processing time significantly increases the overhead, and more results is in the paper. And finally, I summarize my presentation here. First, we present a new idea, and second, we proposed a new problem and a new solution. And third, the new solution exhibits a good performance. And thanks for your attention.